What's going on, everybody? If you are anything like me, pretty much all of the news that is recommended to you by the algorithms is STEM news. And even in the world of STEM news, math news in particular is a very rare occurrence. But this past week, we got lucky and I happened to keep getting this article that I finally took a look at. I thought it was neat enough to make a video and show you what was up with it. It's about deriving the quadratic equation. So that's what we're going to do today. Stick around, it's going to be fun. Before we get started, I just wanted to remind you that if you found this useful or fun at all, make sure you hit the like button down below and subscribe if you want to see more of the same. There's the alerts bell over there, and comment down below if there's something else you want to see or know or whatever. So as a quick refresher, the quadratic formula, yes, the quadratic formula that you may have forgotten largely about from high school, but you might remember that there's like some B's and A's and C's in there, and they're thrown together in some arrangement. But the crux of the problem here is that you have a second order polynomial. So you got something with some squared terms in there, and you're trying to find out where this thing equals 0. Well, the quadratic formula is the thing that gives you what x's you would put into the equation in order to get 0. You might have learned this as finding the roots of the equation, finding the zeros of the equation, something like that. Now, for linear equations, finding the 0 of a linear equation is super easy. If you have an equation like y equals m times x plus b, then this equation equals 0, that is y equals 0, when x is equal to negative b divided by m. The quadratic formula is sort of the equivalent of that negative b over m, but for quadratic equations. And at least in the United States, when you're in maybe middle school or high school, you went through a day or maybe 2 days where they, step by step, they showed you how to derive the quadratic formula, and that almost always included a step that they called completing the square. And now for most normal muggles out there, that idea of completing the square is something that you learn that day in class. Maybe you remember it for a quiz or an exam or something, and then you forget it. And part of the reason that people have sort of a barrier to remembering this idea of completing the square is that it's a little bit non-intuitive. And in fact, it's one of the first times in math that we encounter a very potent concept, which is this idea of adding 0 to an equation in a clever way in order to get a new result. Often students have trouble with this step because this adding 0 requires you to understand what form 0 should take that would be most advantageous to you in order to get, something that you can use out of the equation that you started with. And so just really quick deriving the quadratic formula by hand here, I'm not going to, go over every single step, but you see we get to this point where now all of a sudden we have, our squared term and our linear term, and then there's this constant at the end. And so the question to ask here is there some form of this constant that we could use to turn the equation that we have here into something that looks a little bit more like this? And of course, this would be more handy because now we could just simply move the constants to the other side of the equal sign, subtract them from both sides, and then take a square root, and we're pretty much done. And that's why we call this step completing the square. We're trying to find some constant that enables us to turn all the stuff with x's in it into some squared linear term. We take a linear term and then we just square it. So now the thing that actually made some news headlines in the STEM news world is that there's a professor who came up with a different way of looking at the general quadratic equation that enables you to get the quadratic formula without having to go through the step of completing the square. Let's assume that we're looking at a parabola that has 2 real roots. In other words, that we're looking at a parabola that crosses the x-axis 2 different times in 2 different places. And now let's call those 2 roots P and Q. So if a parabola has these 2 roots P and Q, then we can write the equation in factored form like this. And now if we go ahead and multiply this out and take a look at what we end up getting, we see that we have this P plus Q term. So now equating this with our original equation, we see that we must have that P plus Q equals negative B divided by A. And now here's where the observation comes in. If we were to divide both sides of this equation by 2, then we're looking at p plus q divided by 2 equals negative b divided by 2a. And now the left-hand side of this equation should look familiar. This is actually just the arithmetic mean, or the average of two numbers, p and q. And so now here's where you should put on your thinking cap or get ready to pause it and think about what I'm just about to say. But the insight is that if two numbers average out to be some value, then they must both be the same distance from that value. Or if we want to say it a little more formally, if the average of p and q is negative b divided by 2a, then there must be some number z such that both p and q are z away from negative b divided by 2a. So now this affords us a new way to rewrite p and q, which were two unknowns, using only one unknown variable, z. And now using what we already knew about a and b in relation to p and q, we can go ahead and put these values for p and q into those equations and then solve with what we end up getting, and out pops the quadratic formula, just like we expected. So now I guess there are really two questions surrounding this that, deserve to kind of be thought about. One of them is this really better than completing the square for finding the quadratic formula? And then the other thing is this really something that nobody ever discovered before? That's sort of the claim here, is that this is something new. It's a new insight. Even if somebody has thought of it or, published it, even if that was maybe hundreds of years ago, which seems more likely to me, then I can see that maybe no one has thought to integrate it into modern math lessons. And at least as far as that goes, this is a pretty interesting innovation. But now the other side of it, is this better than completing the square? I don't really know. I mean, I'm kind of torn about that sort of thing. As a person with primarily a mathematical background, so in case you're new to the channel, most of my academic background is in mathematics. That's, what I know probably the best. But I don't know that I like this better because, a very big part of mathematical analysis tends to come from really cleverly adding 0 or multiplying by 1. There are instances of this all over mathematics, and while it is very difficult to come up with the methods that utilize this by yourself, once you see enough of it and do it enough times, you tend to start to get a feel for how you would do this if you encountered similar problems in your own work. And so I think it's still pretty important to teach people, cleverly adding 0. But I do like this as, another way of looking at the quadratic equation that's a little bit different, that might provide students who are frustrated by, adding 0 or multiplying by 1. It affords them a different way of looking at it and a new way of understanding why the result should work. And now in typical mathematical fashion, I couldn't just let it go like that. I had to try to apply similar insights to, say, the cubic equation. And in case you don't know, there is a cubic formula and a quartic formula. So those are formulas for general equations that have, x cubed and x to the fourth terms in them. But there is no quintic formula or above. And not only isn't there one because nobody's found it, but there isn't one because there can't be one. Somebody proved in the early 1800s that it is literally impossible to derive a closed formula that can give you zeros every single time for every possible fifth order polynomial and better. But it is natural to ask that if something works for the quadratic equation, does it work for the cubic equation? And the answer is, I'm not really clear. It might. So if you feel so motivated, I would say have a look at it. You might be able to come up with a really insightful way for deriving the cubic formula from the general cubic equation that sort of mirrors this idea of the quadratic formula from the quadratic equation. All right, so I think that's going to do it for today. I just wanted to do a quick video because I thought that was kind of nifty news. Again, if you liked what you saw here, give me the old thumbs up. Make sure you subscribe down below. We got another video coming up soon where, I'm going to finish off my SMD reflow oven, so stay tuned for that. Hit the alerts bell if you want to get the alerts. Comment down below, and I will see you next time.